sometimes called cubic. Okay, and so first I want to say that so I'll say in this context there exists some g which is a number greater or equal to 0, so that the number of faces is equal to g plus 3. The number of edges is 3g plus 3, and the number of vertices is equal to 2g plus 2, which just follows from the valence 3 property plus or the characteristic of the plane. So ones to have in mind is maybe like a tetrahedral graph or kind of others. Right. So and now the main kind of point I want to grab onto from the graph theory side is I'm going to let I g star of c be equal to the number of face colorings of G using C colors. Okay. Right, and so just kind of something else I'm going to do, just kind of auxiliary thing. I'm going to orient each edge EI, which can kind of be anything at once. And then I'm going to let RV be equal to the number of outward oriented edges at the vertex V. Okay. So now from this, I'm going to do the following thing. So I'll say for each say sort of face vertex pair, I'm going to consider the 3 edges EI, EJ, and EK at V. And so what that's saying is that every time I have a vertex V, which is part of a face, then there are kind of 3 edges, and 2 of them themselves will be contained in the face, and the third one, which I'll call EK, is kind of opposite, not contained in the face. Okay. All right. And so what I'm going to do then is I'm going to, for each face F, I'm going to define del F to be equal to the sum over V in F of EI, EJ, EK inverse. And this will also be signed with -1 to the RV. And so this is the EI, EJ, and EK inverse corresponding to each given V, right? So these will be different for different Vs. Okay. And I'm thinking of this as just like some like formal expression, living in some sort of formal ring or something. Okay, so then from here, I'm going to define x, g, f to be equal to the set of all epsilon mapping the edge set to f star with the property that del fj is equal to 0 for all j. Sorry, let me put n. All right, so what I'm doing is I'm just taking these things that were formal, and I'm just going to solve them over some field and let the set of solutions be some affine algebraic variety, right? So then the theorem that's the sort of intrigue, which is maybe the kind of starting point. So this is due to Sackle. So the theorem says that I'll say for Q equal to P to the M, we have that chi G star of Q plus 1 is equal to, let me make sure I get the constants right. So this is going to be Q squared plus Q divided by Q minus 1 to the G plus 2 times the number of points in XG over field FQ. Okay. So, I want to point out a kind of few interesting things about it. So maybe first of all, the most interesting thing is that I'm not a graph theorist. I'm not a combinatorialist. But this, so Sackle was a student of mine. I suggested this problem to him. But combinatorialists didn't know of this formula before. I'm not sure if they knew of the formula even now, because I don't know if they care what kind of us in geometry are doing. But anyway, so this is something, and it's a bit strange from the point of view of a combinatorialist. For instance, this definitely relies on Q being a power of a prime, so that this is a field. You know, you could multiply through all these expressions to make it positive and then try to solve over like Z mod n for some composite n, but you will get the wrong answer. This is a sort of surprisingly non-linear, I guess, expression of what, of how the chromatic polynomials can be computed, in particularly for like rational points over finite fields. And basically what I want to do is explain not the proof of this, but the motivation for where a formula like this might arise from. Okay, great. So that's the rough kind of context. Maybe I should also say that in terms of sources, so the main thing that I'm going to be citing is a paper with Casals and Sackle from, when was this from? 17. But this is also based on kind of earlier work of Truman and Zaslow from 2016. And then since then, Casals and Zaslow I've expanded this to kind of sort of higher order weaves. So this was in 2020. And then also Sackle has expanded this to non-commutative coefficients and kind of higher rank representations. So I might get a chance to talk a little bit about this. And those are sort of the main kind of directly connected things. This is also kind of more distantly related or inspired by work of like Fock and Goncharov, and also Gallardo, Morin, Mitsuke. Something about spectral networks, but I don't understand those papers, so I won't talk about those. I'll talk about this from kind of a symplectic field theory perspective. Okay, so I'll start with the Truman-Zaslow construction. Okay, so the first thing that you do is, so first, let, maybe I'll call it map U, going from sigma G to S2, be the 2-to-1 branch cover with the branch set equal to the vertices of G, okay? And then I guess we're going to extend this to a map, I'll call U comma Z, mapping sigma G into S2 cross R. So let me discuss this. So and so the basic idea is that kind of near each vertex, we have that U, say U of X is equal to X squared in some coordinates. And so now what I'm going to do is, so very confusingly, X will be a complex variable and Z will be a real variable. So Z now is going to be the real part of, I guess it's 2/3 X cubed, but I'll say here, this is kind of chosen so that the self intersections is equal to the edge set of G, right? So when I'm doing this kind of real part of X cubed, so in terms of the sphere coordinate, which is already like X squared, this looks like, you know, like Y to the 3/2, right? So that's something that kind of goes around in a 2-3 braid. So what this will look like is something like this, where it becomes open. Maybe like that. So kind of something shaped like this, right? So we go, as we go around, we go up, and then down, and then up, and then down, and kind of continue our monodromy that way, right? So that looks like whatever, square root of x to the 3/2. But the point being that we get this sort of choice of where this branching set is, which has to do with the choice of like, what do I define to be the real locus here? And we define that to be exactly this edge set. Okay. And then, so in total then, we get this map here. And so if we, so I'll say map UZ mapping from sigma G to R cross S2, I'll say the image looks like a kind of quilt with seams equal to the edge set, right? So yeah, so we have this some sort of like kind of bubbly sphere, right? Where there's kind of two layers and then there's these kind of pillow regions in between, which then are kind of sewn together at the edge set. But okay, so now what's nice about this construction? So nice properties. So what I'm going to do, so first I'm going to let lambda g be equal to the image of this. So the nice properties, well, so if I take, let's say lambda g tilde, which will be contained inside of R cross T star S2. And so this is the set of all, I'll denote this by Q P Z. So we have Q is in S2, or let me do it this way. Q Z is in it's lambda G, and then we have dz plus P, where here, say, restricted to T lambda G equals 0. So here, this is P, it's in T star S2 at the point. Okay, so this is something that you would call a conormal bundle, or maybe a conormal bundle at infinity. And basically the point is that this is just like all one forms, you know, point-wise, all covectors, which are vanishing on this sort of quilted pillow sort of surface, okay? And since it is the space of all, you know, covectors, which is vanishing on some sort of manifold, it's maybe not surprising that to say that this lambda G tilde is a Legendrian submanifold inside of R cross T star S2, which is a contact manifold with alpha equal dz minus p dq. So I don't want to talk too much about contact geometry, but I think everyone in here has some familiarity with symplectic geometry anyway. So this is a sort of odd dimensional cousin to it. Okay, so first of all, this is Legendrian. Now that works just by the nature of this construction. I could take like anything here and this would work fine. However, now using my trivalent assumption, we get something more. Which is that, so also lambda g tilde is smooth. Just as a submanifold inside of R cross T star S2. And this this relies strongly on the trivalent property. Basically because choosing x cubed is the sort of like next order non-degenerate term. And so this is going to be kind of cut out transversely when you're taking this primitive. However, if you're looking at something which is a higher order singularity, you know, a order 4 valence would have to locally look like kind of x cubed. And then so that won't even be transverse even when you take a kind of primitive lift to first order. So anyway, I won't go too far into it, but it is true that if you try and do this sort of thing for higher valence, it will just not be smooth. And that ends up being significant for us. Okay. And so now I'll say what was kind of like motivating Truman and Zaslow. And so I'll say that consider, I'll denote it, she's lambda g tilde on R cross S2. I'll say this is the category of constructible sheaves on R cross S2. So that we'll say that the rank equal to 1 micro support, singular support, is equal to this lambda g tilde. Okay, so I'm not going to go through all of these words. Like Kashiwara Shapiro is like a pretty thick book. Like, but I was going to give some kind of intuition for this. Okay, so the basic idea is, first of all, we're talking about sheaves on 3-dimensional space, right? But so we're looking at sheaves, first of all, which are locally constant outside of this lambda g. And secondly, we'll say that when I'll say crossing lambda g, the sheaf must change in a sort of prescribed way. Right, so let's say a little bit more about this now. So So let me say what that is. Okay, so first of all, the rule is that if you are including the kind of stalk here, and then you take the inclusion map into here, that's just kind of an arbitrary map. So we have, sorry, this inclusion has cone isomorphic to F. And F like shifted by some grading. I'm not going to talk about Maslow's potential here. And then the other version is like this inclusion, smiley face. One of them is above the surface and one is below. Because we're choosing dz to always be oriented positively, that means I actually am distinguishing kind of positive z and negative z here. And so this one, I'll say this inclusion is, I'll say, a quasi isomorphism, which basically means that I can invert it. So then what that means, if I'm kind of thinking globally, what happens is if I have some piece of surface, and I'll say maybe sheaves also so that I'll say the stalk at z equal minus infinity is assumed to be trivial. So I'm going to assume that. Of course, we can always quotient by that kind of action. But so let's say maybe that this is kind of 0 here, say. And then so that also says that here we have that this is also 0 if I take the stalk kind of at the surface. But then up here, it has to have a cone, which is, just the ground field. And so up here, then it would be constantly equal to kind of rank 1. Okay. So that's the kind of base case. But now maybe we can do a kind of more complicated example. So I'll do a more complicated example, but is maybe down in a single dimension. Okay. So so this is in like R cross S1, maybe example. Okay, so here, this is going to be 0, kind of down here. And then in each of these, well, it has to just be F. Okay. So I'm saying this side is like glued to this side, right? So this is kind of F here. But now when moving from here to here, this is going to be F squared. And so now the other property that will come up in an essential manner kind of in codimension 2 is that, so at transverse crossings, we need a push-out square. So what do I mean by this? So, okay, if I go from 0 to F, maybe that's not so interesting, but let's consider what happens when I'm going from here to here. So not only does this change from F to F2, but we get that if I look actually on the knot, that's the same as the F. And then I have the inclusion map taking that into F2, right? So that means along each of these edges, I have a map of vector spaces, right? So we have maps of vector spaces associated to each kind of crossing. And now specifically, the crossing that we want to take is that if this is kind of A, B, C, D, and then we have these maps kind of here, then what I want is that if I'm going from like A to B plus C to D, that this should satisfy like Meyer-Vittorius, right? Or to say it differently, this should just be a push-out square in the category of complexes. So what does that mean in this situation? Well, in this situation, the only thing we have is just 0, F, F, and then F2. And so to say that those a push-out square is just to say, so say that it's a push-out is to just say that the images are transverse, right? Okay. So then, what does that give us in total? I guess I'm still over here. And then finally, I'll say you might worry that there's like a further higher order condition at the vertices, but turns out there's no condition at the vertices. And so then, so what's our answer? So what is this category? Like, what are the objects of this sheaf category? Lambda tilde G R process 2. And then I'll write modulo isomorphism in the category, right? So this then is just equal to what I'll denote as chi G star taking colors from FP1. And so what do I mean by that? Let's return to this picture. So our picture is going to be in 3D. We're going to have, some sort of surface, which is some sort of quilted thing. But all of the information is just going to be given by each of these maps. And each of those maps is just a line in F2, right? So that means each face is associated with a line in F2, or equivalently, a point in FP1. And since nearby things need to be disjoint, that means that it's a coloring. The only exception to this is that this needs to be modded out by PGL2F, because up to isomorphism, of course, I can act by PGL2 on the F2 on top. Okay, so maybe I'll pause there and just if there's any kind of questions about this. Kind of ran through the sheaf theory, but okay. So this is pretty, I would say, pretty elementary, right? Like, I mean, there's the definitions are very complicated, but the proof is just an unwinding of definitions, essentially. But so now is where the kind of interesting thing happens.
So far, there's nothing that requires F to be.
Yes, I think that's right. I mean, I would have to think about like what exactly is, but yeah, there's nothing here that's yet requiring a field, I don't think so. Okay, so great. So now I want to say like what's the symplectic context of these types of categories? Why do symplectic geometers care about these sort of things like constructible sheaves? And so the basic idea of this, so this is just kind of maybe call this like Nadler-Zaslor review, I guess. So the basic idea is this. So let's suppose that L inside of T star Q is an, let's maybe say, exact embedded smooth Lagrangian. Right? And then so for each Q in Q, we also have T star Q is Lagrangian. Sorry, maybe I should say, so I'm going to suppose that L is a closed Lagrangian, importantly, and so these fibers are not closed Lagrangians, of course. But so what I can do is I can consider the floor homology between L and T star Q at Q. And the idea is that that this doesn't change with Q. You know, if Q moves around, well, it'll move around by a Hamiltonian isotopy, and so I'll get canonical kind of isomorphisms between them. And so what that means is that this whole thing, we could think of this as just a constant, or maybe locally constant in the non-simply connected case, sheaf on Q, right? Yes, say, yeah. But notice that since L is compact, there's kind of not much that can go wrong. Like, now, I'm going to generalize this. And so I guess this is, well, still kind of the same picture, but now I'm going to, so now suppose that, say, lambda inside of the kind of sphere at infinity at T star Q is a Legendre. And now let L inside of T star Q be a Lagrangian, which now I'm going to assume like it's still exact, embedded, and smooth. But what we're going to do is assume that L is equal to lambda cross R plus outside of a compact set, right? So now instead of looking at closed Lagrangians in this manifold, I'm choosing specific kind of boundary conditions and asking them to equal that kind of boundary conditions. Okay, and then the point is that if we look at now the floor homology of L with T star Q at Q, this is again going to be a sheaf, or the stalk of a sheaf. And I'll say this changes only at pi of lambda. So the kind of picture here is that if I have maybe I'll be in T star S1. Here we are, T star S1. And let's say that L is maybe something like this. Say that this is L. And then consider my T star Q Q. And so we see that, so the floor homology is, right, just essentially given by the intersections between L and the fibers. And we see that anytime we move in a way that's far away from pi of lambda, things are going to be like locally constant, but we do have these kind of non-transverse points where we switch, and now there's kind of no things, right? And so, yeah.
So in the picture, what is pi of lambda?
So pi of lambda then would be this point and this point.
Just where it's non-transverse.
Yeah, so but what defines it is that, so lambda is existing in kind of the sphere at infinity. So that's just two circles, right? So it's a subset of two circles, and it's the asymptotics of L. And so really lambda is kind of up here and down here at kind of the sphere at infinity, and then they're being pied down there. But yeah, indeed, it is also the points where it's non-transverse for that reason. But maybe it's only those points where it's non-transverse at infinity is worth mentioning. If L instead was something like this, that doesn't change what lambda is. Okay, so that's a kind of like vague description here, but the thing to kind of impart is why this notion of constructible sheaves, or why this technique of microlocal sheaf theory is relevant to things like spaces of Lagrangians and Fukaya categories. Okay, so okay, so now I'll say there's kind of a sort of general, I don't know, maybe framework for conjectures, like for conjectures, which you might call kind of augmentations, are sheaves. Or more generally, you might say that like a kind of Fukaya category of something of kind of any given type should be isomorphic, equivalent as categories, with categories to a category of sheaves, again, of some other type. And now, so here specifically, so here specifically, say that this sheaf category should be isomorphic to what's called aug plus of this lambda tilde g. And I'll say that, so what actually kind of is this? This is a, oh, I guess I wrote there. I'll say that, so maybe I'll write it this way. Objects of aug plus of lambda, by definition, is equal to the collection of maps epsilon going from the DGA A lambda del lambda down to, say, F0. Let's see, DG A maps. Okay. And I'll say maybe that this is the sort of, in my mind, this is one of the best reasons why anyone should care about contact geometry. So why should a person care about contact geometry? There's the following reason. Let's say you have a symplectic manifold of Liouville type. So that means you have some M lambda, but out here, it just looks like some YC of kind of contact type. So if you want to figure out what is the Fukaya category of M, you might think that that like depends on M, right? But in fact, it kind of surprisingly doesn't. So this, in fact, only needs the geometry, I'll say, outside of a compact set. And then everything else is algebraic. So one way to think of this is that like if I'm doing like floor homology like of a compact manifold or floor homology of a compact Lagrangian, we don't need to figure out what it's isomorphic to. We know what it's isomorphic to. It's just isomorphic to the Morse homology of the underlying space. So compact kind of floor homologies don't really contain any data. It's just the data of the topology. On the other hand, the non-compact business is very geometrically sensitive. However, what we can do is just focus on the geometry kind of here. From here, that gets this algebra. So this A lambda del lambda, I haven't said what it is, but this is an algebra which only depends on the geometric situation here. And then the Fukaya category, this Fukaya category, which this augmentation category is an example of a type of a Fukaya category, is just algebraically given by algebra maps. And so in that way, we can kind of control that. Yeah. So I think that's a good place for the break. And I guess after the break, what I'll do is kind of talk about what this actually is and then how it leads to this formula for coloring, as I said at the beginning. Okay. Let's get coffee.
It's just like a swimmer. You know what a swimmer is? Yeah.
Okay, so I'll go ahead and start again. So I wanted to make a point about this kind of Bukai category just being determined kind of by its boundary. Let's There's kind of an immediate application to symplectic geometry. So this is going back to Truman-Zaslow. And so what they show is that for any G, I'll say like with non-multiple edges, there does not exist an exact Lagrangian filling of this lambda G. And so I'll say the proof. Okay, so first of all, we already saw that chi G star of Q plus 1 is equal to this category of sheaves. Again, mod, or I guess the mod PSL2 is over here with FQ, and then this is going to be times Q squared minus Q, right? Okay, so, but now this is a polynomial, and we even know the leading terms, so we get that Q G star of some number of colors is going to be that number of colors to the number of faces. Maybe I'll denote it F to the total number of faces, and then minus the total number of edges times C to the F minus 1. And then we're going to have plus, something that's O of C to the F minus 2. Okay, This isn't too hard to show. Basically, like if you want to get a coloring, there's just all possible colorings with no adjacencies. These are all the colorings which, have a specified like overlap, right? Like one kind of for each edge. Okay, but now the point is that so, but if L was a filling, then we would get a sheaf associated to each local system, which is going in H1 of L to F star. So I won't talk too much about sheaves, but sheaves have their microlocal monodromy. And so by changing that microlocal monodromy, we can get distinct sheaves kind of by taking local systems on the Lagrangian. And now we know that when we look at the restriction map going from H1 to lambda G tilde with coefficients in F star. So this is just in terms of topology, this is a three manifold whose boundary is a surface, and the restriction map always gives something half dimensional, in fact, something Lagrangian with respect to the cut product. So this has a G dimensional image. And so that means that I don't know if these sheaves are distinct for sure, but if they have a distinct image here, they're definitely distinct from each other because like the monodromy at the boundary is an invariant, right? And so that means that that kind of L exists would imply that that there exists Q minus 1 to the G elements in this kind of sheaf category FQ mod ISO. And basically you compare this to this, notice that E is equal to 3G minus 3. Sorry, 3G plus 3. And you get a kind of contradiction there. Basically that you would have to have too many different colorings for large Q. This is the problem. So what that means then, right, is that that either this sheaves lambda R cross S2 or Og plus of lambda are not actually made of objects who are Lagrangians, but rather they're sort of like FQ kind of algebraic Lagrangians. Yeah, they're sort of, but they're defined purely kind of algebraically. So an actual Lagrangian, if I had an actual Lagrangian, that would define for me a map epsilon associated to L. For every single coefficient field and any other, and it would satisfy universal coefficients. However, if I just fix a coefficient field, I could look for other morphisms which aren't necessarily coming from Lagrangians. And so that's, in this situation, the only thing that even exists kind of here. And in terms of geometrically interpreting what these things are, yeah. Okay, so, all right. Now I want to talk about what this kind of is. So we need to define maybe this A lambda del lambda, and this is something called the Chekhanov Ashberg DGA. And the basic idea of this is to say that, okay, so this lambda, which is equal to this lambda g tilde, is equal to some surface sigma g, which is then embedded into R cross T star S2 as a Legendrian. And then what that means is that if I consider R cross lambda inside of R cross T star S2, that this is a Lagrangian submanifold. And so I'll say then that, okay, so first I'll say that, okay, we have this, but now I'll say on R cross T star S2, we have a Reb vector field, which is just del Z in this case. And so what we'll have then is that A lambda is the algebra. So it's going to be F adjoin words in Reb words. Okay. So what is this saying? So first of all, since the Reb vector field is just del Z, that means that Reb chords, by Reb chords, I just mean a trajectory of this vector field, which starts on lambda and ends on lambda. But since in this example, the Reb vector field is just the kernel of this kind of projection, this is going to be the same thing as the self intersections of, maybe I'll call it pi, but it's a different pi of lambda. So this is inside of T star S2. Okay. Okay, so that's just like a finite set, but now I'm not just taking the sort of span of this, but taking the span of the sort of like full non-commutative tensor algebra over this, right? Like, okay, and then I'll consider what is the differential. So for the differential, what we do, so the del lambda counts, I'll say polymorphic kagons with boundary on r cos lambda, and I'll say exactly one positive asymptotic. Maybe I'll say always asymptotic to red chords, but exactly one positive asymptotic. Okay, so what that means is that we have this picture that we're constantly drawing in SFT, which looks something like this. And so this is mapped, so this is inside R cross T star S2, and see at the kind of the R towards infinity, we're going to get that this is now limiting to some chord, let's maybe call it X. And then I can have arbitrarily many negative kind of asymptotics, which are going to say Y1, Y2, and Y3. So then what we do is we say that del lambda of X is equal to Y1, maybe Y3, Y2, Y1. We get an order because we can go around counterclockwise. Well, I don't know if I read right to left or left to right anyway, but anyway, you get an order by the order of the disk. And then you count up all possible kind of curves. Okay. And so then the theorem naturally is that del squared lambda is equal to 0. Oh. Okay. And indeed, might say also that so these are gonna kind of be going the opposite direction, exactly. This is also, by the way, you can project off both of these R components and just do immersed floor homology in the projection in T star S2 with respect to some certain kind of filtration, and then you can recover everything just down in T star S2 because it's a Dirichlet problem, right? Like in the other two. But yeah. Okay. Right. And then I guess the other theorem is that if boundary L equals lambda, L Lagrangian, then from this we get epsilon L mapping A lambda down to F, which is essentially just counting all polymorphic curves with boundary on L asymptotic to Reb chords, right? And this also satisfies the epsilon L composed with del lambda is equal to 0, which is to say that it's a DG map. This is Gromov compactness for holomorphic curves with boundary on L. Okay, so that's kind of how the general theory works. But for us, there's actually like a lot more, things simplify a lot. in our situation. And so, yeah, maybe I'll just kind of state some things. So this is going to the Casals, Murphy, and Sackel paper. And so this, well, we just kind of like compute things, but I'll say what this is kind of coming from. So the chords of lambda g there are, I'll say, f plus 4 of them. And maybe most importantly, so there's one for each face, Fn. And then there's kind of 4 others, which we call in the paper X, Y, Z, and W, which is well, coming from some geometric thing that I don't have time to talk about, has to do with we're taking this space R across T star S2 and embedding this in a natural way into R5, and we're actually kind of working there, but that embedding induces some other sort of chords. I could say more about that if there's time, but maybe there won't be. And in fact, we can get that del W is the external face. So what we can do is we could also instead just, get that there's f plus 2 of them instead, by canceling those out. You can even cancel them geometrically. I'll ignore that though, that kind of doesn't matter. So the question now is, what are the EIs in this setting? So my original formula was in terms of EIs, right? So we should think of EI as living in H lower 1 of sigma G, right? Because if I have an EI like this, then locally to it, I'm looking at a 2-to-1 branch cover over 2 points, right? 2-to-1 branch cover of the disk over 2 points. So this is an annulus. And there's a homology class associated with this, kind of the one that goes on the upper branch here, and then goes in the lower branch here, and back on the upper branch, back on the lower branch, right? So that's non-contractible in the kind of annulus, which is local to this picture. And so, so the point is now is that all of this either can, or even better, should be done with maybe h1 of lambda or even pi1 of lambda coefficients, because I have these curves anyway, right? Their boundary is living in R cross lambda. And so I should keep track of that data. And if I keep track of that data, then that gives me coefficients in this kind of larger coefficient system. And so when we write del F is equal to the sum of this plus or minus EI, EJ, EK inverse, what is that kind of coming from? This comes from the fact that if I'm looking in the graph, right? So let's say I have some graph like this. And so you got to imagine this is, I'm looking at it from the top down, but in 3D, this is some quilt thing, right? So I have like some like pillow thing inside of here, right? So the reb chord will be kind of right in the center of the face, which is going to be where the difference function of the pillow, the kind of top minus the bottom, has a local maximum, right? And then so what holomorphic curves, maybe I'll say hollow curves in the limit are equal to kind of gradient trajectories of the sort of delta height functions, and then just like times del z, okay? So for maybe kind of a simpler example, if I have maybe something like this is just in 2 dimensions. So we're going to have a single reb chord here, coming from a critical point of the difference, kind of another one here. Oh, and there might be even a, I think that's right. And then so we'll have a holomorphic curve. It's kind of this like vertical wall, which is going from this critical point to that critical point, is just kind of like z times just the Morse function. Okay. So in particular, we get that there are 4 gradient trajectories of this difference function, which limit to the corners. And so those are the 4 holomorphic curves, which have a positive boundary puncture at F. So we have that kind of in this picture, in the style of those pictures, we have just one that's going along Fj, and then it's just a filling by a disk, no negative punctures. But this term, EI, EJ, EK inverse, is corresponding to the fact of like, how do you intersect that cycle? How do you intersect that cycle? And how do you intersect that cycle, right? And so, well, it is what it is. All right. So maybe I'll just, let me say kind of a few more words about this. So, so here, what do I want to say? Okay, maybe gradings here. So it'll turn out that the grading of any f is just equal to 1. The grading of any homology coefficient should be 0, because these are Maslow's 0 Legendrians. And finally, we have that the grading of this x, y, and z is actually grading 2. And so the point is that these maps epsilon, which is mapping kind of a lambda del lambda down to f0, this is required to be a DGA map. In particular, not only is it required to be a ring map and send the differential to 0, it also has to be a graded map. So since this is a graded map, we can have that epsilon is not equal to 0, kind of only on these kind of EIs, right? And so that means that this is kind of the only thing that matters, right? We're going to have some other terms which is going to be of the form like del x is equal to a kind of, polynomial, a polynomial in the EI times Fn times another poly in EI, and this will be the sum over n, right? However, none of this is all in degree 1, and so it doesn't affect the map epsilon at all, right? Like, okay, yeah. What else do I want to say? So maybe the final thing is that we had chi g star of q plus 1, or I'll even write this chi g star in fp1, so taking colors in fp1, we said was isomorphic. Let me actually switch back to q plus 1. So we said that this was isomorphic to q squared plus q over q minus 1 to the g times the number of solutions in this xg fq, right? So this was this result. So I want to say what these other sort of factors are here. So so first of all, better to write this. Oh, sorry, and this was g plus 2, I think. It's equal. These are integers. So better to write this as q cubed minus q over q minus 1 to the g plus 3 times fg xq. But so the q cubed minus q, we probably recognize as the order of PGL2. But then what's the kind of rest of this? So notice that okay, so first of all, q cubed minus q, that's equal to the order of PGL2F q. Great. So the q minus 1 to the g plus 3, this is going to be the order naturally of fq star to the g plus 3. So let me talk about where that is kind of coming from. And so what we can do is I can well, what do I want to say? So I'm gonna, for a face fj, I'm gonna define phi fj going from this algebra where I adjoin t to the plus or minus 1 and back to itself. And so what I'm going to do is I'm going to define phi fj of ei is equal to TEI if EI is contained inside of FJ, and it's just EI else. Okay. And then I also have that phi FJ of F is going to be equal to, I think, T squared F, wait, This can't be right. It must be the other way. Yeah. Oh, no, this is right. Yeah. So t squared f equals fj, and it's just equal to f else. Okay, and then yeah. So the idea now is that all of those maps I don't really know. I vaguely know, but I think it'll maybe become a little bit more clear as I talk. Yeah, and so I'll say that all BF mute and also all BF circ del is equal to del circ BF. And so what we can do therefore is we can let say maybe F's let maybe a underline be equal to phi in z to the g plus 3 variant algebra. So we have this sort of, it's some sort of like gauge symmetry to this situation. And I could say roughly kind of what it is. The issue is that the edge set is actually equal to 3g plus 3 edges, but of course, h1 of sigma, its rank, right, is just 2g. And so we have kind of g plus 3, extra generators kind of h1. And so for some reason, I don't understand why there's kind of a gauge group acting, but there is some kind of gauge group acting, which is kind of killing off this kind of indeterminacy. Kind of specifically, I guess the lemma is that, okay, so take any v in the vertex set and then let t as a subset of the edge set be a tree spanning v minus v. Now, the nice thing about this is that these two conditions will imply that this is actually just 2g. And furthermore, so the lemma says that for any beta which is mapping, say, e minus t to z, I'll say there exists a unique phi in z to the g plus 3, so that phi of ei is equal to t to the beta of ei times ei for ei in edge minus 2. So this is a sort of Coulomb branch of this gauge action, right? Like, so the point is that if we just choose this kind of spanning tree, then that immediately not only is the order of this 2g, but in fact, this will span h1 of the surface. And furthermore, if I kind of just set all of the other EIs to 1 and then just use the ones in T, then that will work fine because that's some sort of gauge fixing condition rather than a gauge quotient, right? Like, so the point is then is that that following from this lemma then implies that a bar del, so the ones that's actually invariant, is going to be isomorphic to, you know, A with coefficients you know, with this statement that EI is just equal to 1 when EI is not in T. Okay, so this is pretty, I guess, sort of elementary, but it's exactly that then, which naturally is acting by this kind of G+3 order torus, which then explains this quotient, because the one that's actually kind of like symplectically natural is, you know, the one that's actually over homology coefficients. Okay. So from here, let me see. Maybe I'll just give a couple more comments. So to my mind, there's kind of at least a few kind of questions. So one is that the space of kind of objects of, you know, in this, say, log plus, lambda plus. So this is contained inside of H1 of lambda with F star coefficients. And in fact, it's not too hard to show that in this example, and probably in like every example in this dimension, that this is actually Lagrangian with respect to kind of cup product. Right, cup product's a symplectic structure here since this is a surface. So one question is kind of like, so what? Right, like, so that tells me that like, maybe we should try and do some floor homology on this moduli space of objects, right? But like, is that meaningful? Does it mean anything? Probably also this should be thought of as a holomorphic Lagrangian, so one might have to get into that. So that's a kind of other thing. The other thing I would say is that we also have this additional algebra going from the x's to the these other terms here. And the point is that yeah. Sorry, lambda. Oh, yeah. that shouldn't be there. Yeah, thank you. Maybe here I should put lambda g because this is not, you know, for arbitrary lambda, you could also have index 0 chords, which is part of this, but for these, there's no index 0 chords. Yeah, so the question is kind of, what is this good for? Kind of, if anything, like it's data, like it definitely is kind of picking up more data and it's explicitly computable. So in the paper, we kind of lay out how to compute this. But since it's not involved in the sort of augmentation variety, it's not clear what its meaning should be, I guess. Right, and yeah, maybe finally, I'll just notice the following thing, just as a sort of intrigue or whatever advertisement. So I'll say Sackel in 21. So he extended the computation of A lambda G with H1 lambda G coefficients to pi1 of lambda G coefficients. And the reason why that is sort of relevant is because there's certainly another type of sheaf we could consider. And that sort of sheaf is like, what if we had something where like this was 0, and then here it was already like F2, so the cone was already like 2-dimensional, and then here the cone was again 2-dimensional, so that's like F4. And so now we have two planes, right, inside of F4, and so now we're coloring with like the 4-2 Grassmannian, except instead of adjacent faces needing to have distinct colors, they have to have transverse colors. So that's a new type of chromatic graph theory, but now the point is that throughout all of this kind of augmentations as sheaves isomorphisms, what should this correspond to? This should correspond to maps epsilon, which are mapping A lambda G del lambda rather into kind of F star. It should now be mapping into GL2 F 0. And in general, right, so such a representation will give a sheaf so that the kind of local cone is identified with the, the space the representation is acting on, right? So anyway, that's just to say, now the point is that since this is non-commutative, it's very important to keep track of the full non-commutative structure here. And in particular, we have to be using pi1 coefficients rather than just h1 coefficients. But in this way, so Sackel shows that that this space of epsilon is gives a bijection with the space of kind of say 2n n Grassmannian colorings, transversal colorings. Jeez. So that's one kind of extension of this to some non-commutative territory. But yeah, I think I'll stop there. Thanks for listening.
What happens if you let go of trivial graphs? You know, all the graphs.
Yeah. Basically, I would say the shortest answer is I have no idea. In that, if you have this kind of 4-edge thing where you have this sort of pillow going to it, so one could certainly kind of define that. But the problem is that the resulting lambda G existing in kind of the sphere bundle, say T star, whatever, R3, this won't be smooth. And for non-smooth things, I just don't know if any of this kind of augmentations or sheaves isomorphisms happen. Sure.
When we work with these higher rank sheaves, if we take like instead of finite fields, we work with like complex numbers. Is interesting to work with like
Yes, yeah. So something I should say is that this result about this result here. So this result can be generalized to, if I'm doing chi G star, where colors are taken from FP1, and then I mod out by PGL2F, that this will be isomorphic to XGF modulo F star to the G plus 3. So the point I'm making is that this statement, which implies this statement for finite fields, is actually true for all fields on the level of like varieties, not just like bijection of points. So that's the rank 1 case. This will also be true in the higher rank case for F could be C or anything else.
Where do colors live here?
In the 2NN Grossmanian, but then with this additional condition that two adjacent colors are not merely required to be distinct, as n-planes, but transverse as n-planes, right? And so that's a different notion of what a coloring is, but yeah.
No, I was just gonna say, we meant to ask Sasha about his availability, but. it's not here. Yes. Seemed to remember him saying something about he was away part of January. Maybe. Did you see Gerber's email though?
Yeah, our phones, what's available?
Yeah, we have nothing booked for next time, so I wanted to ask, do you have any preference?
No, I don't know.
Okay.
I just answered.
Sure, but you haven't know if Sasha,
No idea.
okay, because I thought meetings at something about not being here in January, but
Okay.
I didn't have that chance.
I don't know.
Fair
Sorry,
enough, okay.
sorry. I
Yeah,
have to
that's
run.
fine. We can ask him tomorrow, I guess.
Yeah,